What if I told you there's a rule in math so simple you'd swear it had to be true, yet accepting it might let you tear a ball into 5 pieces and reassemble it into 2, or make some line segments suddenly have no length at all? This rule didn't just challenge the math, it nearly destroyed the man who believed in it. Welcome to the paradox-filled world of the axiom of choice, a mathematical idea so controversial it caused decades of chaos and almost broke one of history's greatest minds. The story begins not with numbers, but with choice. In everyday life, choosing a number like 42 or 137 feels natural. But in pure mathematics, randomness is an illusion. Every decision must follow a strict rule. That's why computers can't truly generate random numbers. They rely on time-based algorithms that only simulate randomness. But in math, if we can't randomly choose, then how do we choose at all? Mathematicians tried to create rules, like pick the smallest number. That works fine with whole numbers. The smallest positive integer, 1. The smallest prime, 2. But now, try doing that with the real numbers, those infinite, densely packed points that include fractions, irrationals like p, and even numbers like 1.001. Try finding the smallest number after 1. You'll be trapped in an endless loop. There's always a smaller number closer to 1. This is where infinity begins to push back. In 1874, a German mathematician named Georg Cantor asked a simple but profound question: are all infinities equal? Using a revolutionary idea, diagonalization, he proved that some infinities are uncountably large, like the real numbers, while others, like the integers or rational numbers, are countable. That meant some infinite sets were fundamentally bigger than others. It was a shocking discovery. Cantor pushed further, trying to well-order every infinite set, even the uncountable ones. That means organizing them in a sequence with a clear first element, and every subset also having a starting point. He succeeded with countable sets like integers by defining an order: 0, 1, 1, 2, 2, and so on. But ordering the real numbers was a mountain he couldn't climb. Still, he believed it could be done, not because he had a solution, but because he believed God guided him. That belief, however, would cost him dearly. His former teacher, Leopold Kronecker, turned against him. Academia shut its doors. Cantor was mocked, rejected, and eventually suffered repeated mental breakdowns, leading to stays in sanatoriums. The man who discovered different sizes of infinity could no longer find peace in the finite world. Then came hope. At a math congress in 1904, a professor named Ernst Zermelo heard an argument claiming Cantor's well-ordering theorem was wrong. But something didn't sit right. Within 24 hours, Zermelo exposed a contradiction in the argument. And just weeks later, he published a paper that would change everything. Zermelo had completed Cantor's dream. He proved the real numbers could be well-ordered. But there was a twist. Zermelo's proof didn't construct the order. It didn't show how the real numbers could be arranged. It just proved that somehow it's possible. How? With the help of a bold new assumption, the axiom of choice. This axiom simply states that if you have infinitely many non-empty sets, you can choose one item from each, even if there's no explicit rule to do so. It's obvious for finite sets or infinite ones with a rule. But for uncountably infinite sets with no rule, that's where things get weird. The axiom made Zermelo's proof possible, but it also opened the door to disturbing consequences. In 1905, Giuseppe Vitali used it to construct a set of real numbers, now called the Vitali set, that had no measurable length. You could shift and replicate this set infinitely, and the math would break. It would demand that something with no size somehow fills space. The only explanation? These sets were non-measurable. Their size literally couldn't be defined. It got stranger. In 1924, Banach and Tarski used the axiom of choice to prove something that sounds like a magician's trick. You can take a solid ball, split it into just 5 pieces, and reassemble them into 2 identical balls of the same size as the original. Do it again, now you have 4. And again, now you have 8. Congratulations, you've just created an infinity of balls from 1. How? By splitting the ball into fragments so complex, so abstract, that they defy measurement. These pieces are non-measurable too, and they only exist because the axiom of choice allows you to select infinitely many points in ways you can't describe. It's mind-bending. You begin with a single ball and end with an infinite number, violating everything we know about volume and space. Mathematicians were horrified. The axiom of choice was too powerful. It solved problems, yes, but it also broke reality. Some argued it shouldn't be allowed. Others insisted it was essential. Debates raged for over 30 years. Was the axiom just convenient, or was it dangerous? In 1938, Kurt Gödel proved that if all the accepted axioms of set theory are consistent, then adding the axiom of choice wouldn't cause contradictions. In 1963, Paul Cohen proved the opposite. You could also build a valid version of mathematics without the axiom of choice. Just like how geometry changes when you alter its 5th axiom, math can take 2 parallel paths, with choice or without it. So the real question isn't, is the axiom of choice true? The question is, what kind of mathematics do you want to create? Today, the axiom is widely accepted because of its power. It simplifies proofs, reduces complex theorems from 20 pages to half a page, and allows generalization to infinite cases. But it comes with a cost, a loss of clarity, an embrace of paradox. Some mathematicians still prefer proofs that don't rely on choice because they provide deeper insight into how results are derived. Others explore what math looks like when choice is removed entirely. But for most of us, the axiom of choice is a silent partner, used constantly without even realizing it. Like gravity or language, it becomes part of the environment, invisible but essential. In the end, the axiom of choice didn't just rewrite the rules of math. It revealed the boundaries between reason and belief, between logic and paradox. It showed us that in the infinite, sometimes truth itself